All right, today what we're going to talk about is Latin squares. And we're talking about Latin squares, and if you're watching a YouTube video, obviously you're just going to see that. And then if you're listening to the podcast, you're going to hear the YouTube video, the Latin square, and then we're going to do empty cells. But first I'm going to tie up my shoe so I do not fall over and die. I doubt I'd die. But, right, so let's see, what else do I have to, there it is, okay, good. So, this is a weird design I'm going to tell you about. I've had a student use it once who worked with me, 15 years ago. That's about it. So we've discussed procedures for dealing with a nuisance variable, blocking, right? Remember the thing about maybe people had different experiences with French, so maybe they would have done, like if they were in immersion in school or some such thing, maybe they would do better in a French class or some such. So we use that as a nuisance variable, okay? And we just cut it out, basically. Well, that's what blocking is. Repeated measures, of course, the ultimate example of blocking, the special case of blocking, you're blocking on the subject, right? So you use someone as their own control. So that's two cases where we use, where these nuisance variables come up. You also can do something, I talked about this very briefly the other day, called ANCOVA, where you take it out as a covariate. It's a statistical technique that I'm not going to talk about, but it's something you can do, okay? There's nothing wrong with it, it's just beyond the scope of the course, really. You'll find out about it in grad school. But you could do that too. It's just a different approach. Now, what if you have two nuisance variables? And that's quite possible. So let's say you have whatever these two nuisance variables are, and a third variable, and that's the independent variable, the one you're actually interested in. Remember, nuisance variables are real variables. We just want to remove their variance. So if we have two of those and one independent variable, we may be in a special situation where we can use a special design. We are going to basically put all of these things together, the two nuisance variables and the levels of the independent variable, and come up with a really cool research design that works under very specific circumstances. So we're going to put one, I don't know why I've got so many exclamation points, I'm sorry for thinking this is exciting. So we would have one nuisance variable in rows, like we would normally do, and then one in columns, and then levels of the independent variable in individual cells. So I'll show you this in just a second. But I think you can see you have to have two variables that are nuisance variables, and they both have to have the same number of levels. And it's going to have the same number of levels as levels of the independent variable. This is very restrictive. It's very restrictive. And I'll give you an example in a moment, and you'll see what I'm talking about. Okay. So, like I said, it's not as exciting as I think it is, but it's getting near the end of the course, so it doesn't feel like it because it's minus 14 now. Why is it that cold on the 18th of March? I am not happy with that. I don't normally complain about the weather, either. I'm not that person, but that's enough. Right, so what you get is this thing here. Oh, that's neat. Now, what this is weird. Now, it's weird in a lot of ways, and this is standard sort of notation, and I apologize because it's going to confuse you. The 1, 2, 3, 4 on top and the 1, 2, 3, 4 along the side are different levels of two different nuisance variables. Or two other variables. The case I'll talk about, the thesis student, actually wasn't a nuisance variable. And then we have that A, B, C, and D are different levels of an independent variable. So A, B, C, and D in this case, just with Latin squares, are not different independent variables. Okay? This is a special design. It's sort of off to the side of all the other things we've talked about. So we still analyze it with ANOVA, but it's its own thing. It's its own thing. Okay. Let's just move that over there. There we go. So A, B, C, and D, again, are levels of a factor. They're not different independent variables. They're like A1, A2, A3, A4, that kind of thing, okay? And each level occurs in each ordinal position. Note that the A occurs in position 1, position 2, position 3, position 4. The B is in 2, 3, 4, and 1, etc. And each row, each column, has each level once. So A occurs in column 1 once, and in row 1 once. B occurs in column 3 once, and row 2 once. Okay? You can see the easiest way to construct these things is just go like A, B, C, D across across, and then just move them over. You don't have to do it that way. There actually are tables of Latin squares, like in the back of stats books, if you ever need one. But typically, I think people just do this. So, you need equal numbers of rows, columns, and independent variable levels. This is incredibly restrictive. And this is the model. X equals mu plus alpha plus beta plus gamma. Delta, I'm sorry. Delta, alpha, beta. No, gamma plus epsilon. Alpha, beta, gamma, epsilon. You'll note there's no interactions. There can't be because we don't see all the levels don't occur with all the other levels, right? All the variables don't occur with all the other ones. So any score equals a grand mean plus the effect of rows and columns, and then we're interested in the independent variable. That's what we care about, is the IV. And of course, we have error that's left over. We can call that residual, which is typically the term we use with Latin squares for some reason. I don't know why we use it here more often. Okay. So again, you'll notice there's no interaction. We have 3 variables and no interactions. If all of those levels, we would have a 4 by 4 by 4. So we would have, in fact, instead of 12 subjects, because each person occurs in each cell, instead of 12 subjects, we would have 4 by 4 by 4. That's 64. Okay. You can see that it saves you a lot of time, but you better be sure there's no interactions. And there are special cases where this occurs. All right. So the ANOVA just looks like this. Rows and columns each have p minus 1. P is the number of rows, P is the number of columns, P is the number of levels of the independent variable. They are all the same. P minus 1, P minus 1, P minus 1, P minus 1 times P minus 2. So if you ever see on a quiz, for example, or a test, where I give you this table and I ask you, could you give me the design? If you see the words rows and columns, the only thing it can be is a Latin square. It can't be anything else. So don't rack your brain and go, oh, what could that be? Wow, it's a Latin square. It's got rows and columns. And you look and go, so let's say it says p minus 1 there. So if these are all 3s, then it's a 4 by 4 Latin square. If they're all 2s, it's a 3 by 3 Latin square. If they're all 93s, it's a 94 by 94 Latin square. Okay? So as soon as you see rows and columns, the only thing it can be is a Latin square. Now, there's one time in my career where I found this useful. A student who did an honors thesis with me. And what she was doing was trying to detect if people could, in different combinations, smell dangerous chemicals. So we had, now they weren't super dangerous, obviously, we had people smelling them. But they were things that were poisons, gasoline, stuff like that, okay? But if we mixed in, this was her idea, what if we mix in other substances that are pleasant? Do they mask it or not? It's a cool question, actually. Now, she found 8 things to identify, and then 8 noxious smells. And I said, so you want to do it 8 by 8? So you want 20 subjects per group, so you need 2,560 subjects. Do you want to do that? Or do you want to do 8 by 8 with 64 people in a Latin square? And that's what we did. So instead of having to have 64 groups, we had 64 people. And they went in and they would smell these combinations, and so the person would come in and they would have a combination, let's say A and J, or whatever it was, A and B or whatever. And let's say that is, I'm going to make something up here, ammonia and vanilla. But that's all they get, and you're just told, what do you smell? And you're done. That was how the experiment worked, because if we wanted to do an 8 by 8, we'd have an 8 by 8 design with, like I said, let's say 10 subjects per group. That's 2,560 people, right? There's 640. It's a lot of people. So 64 was a lot easier. So, and I think many of you have heard your colleagues in 4th year talk about how hard, how hard it was to get subjects this year. Finding hundreds of them would have been impossible. So under very specific circumstances, These designs are great, but in my career, I have supervised 104 honors projects. I've run countless projects of my own. I've seen this used once, but it is useful under very specific circumstances. So some conclusions about Latin squares. These designs, as I said, super useful if you can meet their rather stringent assumptions, which is equal number of rows, columns, and levels of independent variables, and no interactions. That's not always easy to meet. And how do you know there's no interactions? Hope. Previous research, hopes and prayers. I mean, that's all you got. Mostly thoughts and prayers is all you got. Okay? So questions about Latin squares before we move on to empty cells. So it's a very specific thing. Remember again, if you see a quiz and it says columns and rows, it's a freaking Latin square. Don't try anything else. Okay? All right. So